So look at that. We usually think that the circulatory lift and circulation, they are the same thing. There is a transfer function in between. And if there is a transfer function between, we tend to think, right, physics, the physical intuition will tell you that when the circulation is generated first and then left, right? According to this model, it's the other way around. Do you remember what's this guy? E to the negative s. What's e to the negative s? Do you remember this? It's a delay. There is a difference between lag and delay. Delay for 1 second means the system is doing nothing in 1 second. Lag of time constant 1 second meaning the system is rising and will reach some certain percentage of the output in 1 second. Okay? There is difference. Delay is really doing nothing. Delay is delay. Okay? Lag is just you're slow a little bit, but you're rising. You're continuously rising. So this is a delay. We have a delay and we have an integrator. So as B goes to 0, so the low frequency limit, you're oscillating low frequency. This guy goes actually, look at just Bessel function. You will see that this guy goes as 1 over P. So P goes as 1 over P, and you will have the relation between rho u gamma and circulatory lift goes as a delay. There is a delay in the low frequency limit. So if you're oscillating with frequency, according to this model, the circulatory lift develops first, and then after a little bit of a delay, the lift due to circulation, or the circulation develops. This is all because of the confusion due to the fact that the circulatory lift is not left due to circulation. It's left due to circulation plus some instantaneous terms, acceleration terms that have no lag, no dynamics. The high frequency limit, this guy goes as actually cancels this, and we have square root P. So at the end of the day, this transfer function will behave like 1 over square root P or 1 over square root S, which explains the 45-degree kind of thing in the high frequency limit. It's a fractional integrator. Integrator, it's delay kind of, right? Integrator is delays kind of thing or lags the response. And the delay, of course, is just a delay. So anyway, in both the low frequency range and the high frequency range, from the circulatory lift to circulation, there is either a delay or an integrator. Both imply time lag or time delay between input to output. Yes?
Is the delay attributed to the viscous nature of the flow?
No, this is pure inviscid. But we took viscosity into account into an indirect way, which is through the cutter condition. So the way we took into account, yes, it might have caused this delay, but I'm not sure about that. If you take into account the viscous effects, like we did recently, our paper is still under review, you will see more lag. Apparently, from the get-go, you account for viscosity, you get more lag immediately. Okay. So anyway, I think we covered this point. Hopefully, I will come to here later on in the course and show you how. But anyway, if we don't have time, here is the paper. It's a very interesting paper, and it uses the language that we built in this course, dynamics and control. And you can replace the very lengthy derivation of Tedorson that we spent 3 lectures just like this in the language of dynamics and control. Hopefully, we'll try to show it later in the course if you have some time.
Question.
Yes.
Can you repeat again how you obtain gamma uppercase over LC?
This thing?
No,
Oh, here?
No line.
Yeah. So gamma over left is gamma over gamma quasi steady.
Yeah.
Multiplied by gamma quasi steady over left, right? This guy is the gamma transfer function. Okay?
Yeah.
And this guy, the transfer function from gamma quasi steady to left is the same as from left to quasi steady to left circulatory. The difference is just rho u. So this is indeed. Remember what is the main input to Tedorson? This is Tedorson circulatory lift, right? What's the main input to the dorsum? Well, it can be angle of attack at the 3/4 pole, it can be quasi-steady circulation, it can be quasi-steady lift. They are all the same, right? There's just a constant multiple between one and another, right? So this is the transfer function between quasi-steady circulation and circulatory lift. This is the dorsal function. So you have here C of K, this is this guy. So this is, I'm sorry, this is the 1 over C of K, because the lift is down. So you have this guy and divide by C of K. This relation in particular, hopefully we'll derive it maybe next time or so. This is not, it's not in Peters actually, it's another place. But Peters shows this very, very clearly, and I believe it's the only place where it shows this thing. That, you know, the circulatory lift is not lifted into circulation. Which is very confusing. The name actually, the name says that it's circulatory lift. Anyway, let's go now and talk about the meat of today. I mean, these things are not the meat, but anyway, we'll have useful stuff. Finite state approximations. Like Riaz was asking, okay, why do I need the transfer function? I already have the frequency response here, because the frequency response is not that convenient. Okay, the frequency response, where is our frequency response? Tidorsum. This is Tidorsum. It's not very convenient to compute. It's not very convenient to simulate. I want to get the output due to an arbitrary time varying input, arbitrary time varying angle of attack. This is quite hard to get it from here. I mean, this is not meant to deal with, this is simply in the frequency domain. If you're asking something in the time domain, this is not the right place to go, simply, okay? So this is why we have the state space model. It's the equation that system dynamics is written in the time domain. We have three things. Representation in the time domain, this is state space model, x dot equals ax plus bu. We have representation in the Laplace domain, this is the transfer function. And we have representation in the frequency domain, each of these things has its own uses. If you take a course on robust control, all what they do here, it's here. Even in the baby control, sometimes we design the control in the frequency domain, the lead and lag and all of this, right? Sometimes we design in the Laplace domain, like the P, if you have a root locus, if you have just a proportional gain, right? We design in the root locus in the Laplace domain. State feedback design is in the time domain. So each representation has its own uses, but the most generic one, the most convenient one to dynamics and control people, actually a paradise for a control engineer, is state space model. Okay? What is the issue here? Well, if you have a transfer function, I can get a state space model. Remember, there is a command in MATLAB, transfer function to state space of whatever. Give it the transfer function, we'll return the state space like this. It's not a big deal. Why am I making this a big deal? Because of the following. How do you know the order of your system? How do you know the order? If it's second order, third order, fourth order, how do you know the order? How do you know the order? Any idea? It's not that deep, it's very like this. How do you know the order of your system? How do you know the order of your system? Look at what? If I give you a system and I ask you, what order is that? Where are you going to go and look? Come on. How do you know that you have a second order system or a third order system, fourth order system? You simply look at the denominator, right? And you get what? You get what? What do you get from the denominator? The poles. You get the poles. You have 3 poles, third order system, 4 poles, fourth order system, and that's it. So the order of the polynomial here, which is exactly equal to the number of roots, which we call poles, this gives you the order of the system, right? Okay. What order do you expect for this system, for this unstable dynamic system? Remember, the order of a system represents the number of degrees of freedom, right? For a motor, we have 2 states, current and angular velocity. So these are 2 states. It's a second order system. If it's It's a mechanical system. Usually the order is double the states because we have position and velocity. So always the order of the system is related to the number of degrees of freedom. So what order do you expect to this flow dynamical system? What order do you expect?
As many particles as there are
Which
is infinite.
infinite, exactly. If you go and look at the roots of this complex, very complicated function, Bessel function, it has infinite number of roots. It has what we call a branch cut. So a line, a continuous line in the complex domain, every point along that line is a root for that function. So yeah, we have infinite number of poles. It's not that useful at all. It's not only because it's a frequency response, but it's an infinite dimensional frequency response. And this kind of expected. At the end of the day, we're solving a PDE, Laplace qualifier equals 0. We're not solving an ODE. If I'm solving an ODE, well, if I have triple dot in my ODE, 3 differentiation, it's a third order system, right? If I have 4 dot, it's a fourth order system. But at the end of the day, this is a PDE, it's not an ODE. So it's an infinite dimensional system. So this is expected, and indeed, if you take this function and look at the roots, it has a branch cut, it has infinite number of roots, we have infinite number of poles. This is not so useful at all for dynamics and control applications.